Before starting the session, I would like to introduce our guest, the session chair, Dr. Pankaj Pandey. Dr. Pankaj Kumar Pandey holds a bachelor and master's in chemical engineering from the Aligarh Muslim University, Aligarh, and PhD in chemical engineering from Guru Gobind Singh Indraprasth University, Delhi. Currently, he is working as a deputy director of the Amethi School of Engineering and Technology, Amethi University, Rajasthan, Jaipur, and head of the Department of the Chemical Engineering. He has a total academic and administrative experience of more than 20 years. He is member of Board of Study of Chemical Engineering of different universities, life member of Indian Institute of Chemical Engineers, member of Institution of Engineers, Indian Desalination Association, and various other professional bodies. He is editor-in-chief of International Journal of Chemical Concepts, editorial board member of the Asian Journal of the Chemical Engineering, and the reviewer of various SCI and Scopus Index journals. Presented paper in many international conferences held in Singapore and Italy. His area of research is adsorption engineering, heat and wastewater treatment, published research paper in various international and national journal of repute. Thank you so much, sir, joining the session. Now over to Pankaj, sir.
Thank you, Dr. Rajiv Sharma ji. So we have 5 participants for this session. Ekta Chandravanshi.
Sir, basically only one candidate is there, that is Ajitha Mary.
Okay.
Rest others either will join or they may be absent.
Okay.
Okay,
So,
good morning.
Then Ajitha, you have full time for you.
Oh, okay, I will start my presentation, sir.
Yes, you can.
Sir, are you able to see my presentation?
No, not yet. No, not is visible.
Is it visible, sir, now?
No, now visible.
It's visible.
Yes, sir. So I'm just starting with this, my presentation. My topic is crystal growth and characteristics of stoichiometric sp2Te3 XS6 platelet crystals. Actually, under the guidance of Dr. Premlata Pandit, Dr. Ritesh Yadav, Department of Physics, Dr. APJ Abdul Kalam University indoors. So the introduction about my paper is crystal growth actually becomes one of the most intriguing disciplines in material science due to the fast improvements in semiconductor device technology. Although many factors involved make it a difficult process, the numerous methodologies and preparation of vapor crystals are actually compliant. Consequently, crystal formation from vaporization is a majority part of optoelectronic and thermoelectric research. So this paper mainly provides the growth of platelet crystals sp2Te3 XSX with the 0.1, 0.3, 0.4 X values followed by structural, chemical, morphological, thermoelectric, and mechanical properties of first-grown crystals. To begin with the antimony telluride crystal, the dazzling, colorful look with the new and distinguished crystals from which the mineral world is actually new qualities for distinguished crystals from the mineral world as intriguing things for all. A substantial chunk of current semiconductor hardware's operational capabilities is dependent on active or passive crystalline core parts. In this perspective, antimony telluride is one of the most candidate of group 5 to 6 deserves a prominent position as it shows different thermal electrical features appropriate for thermoelectric applications. So main problem and here is growth of platelet crystals sp2Te3 XS6. In recent years, thermoelectric energy conversion technology has enriched much interest because of the global energy shortage and environmental concerns. Consequently, significant progress was sought in the development of thermoelectric high-performance materials. Pure and doped sp2Te3 compounds are now the most famous thermal control materials for micro and optoelectronic devices. Research on their electrical and structural characteristics is thus intriguing for applied and fundamental research. So growth of platelet crystals, sp2T3XSX, the strong demand for bulk thermoelectric with a figure of merit greater than 1 is present in the temperature variation from 300 to 800 Kelvin, and the high Seebeck coefficient, low electrical resistance, and thermal conductivity are beneficial. According to sp2T3 is an electrically conductive conductor of more than 300 per meter and a value less than 0.3 owing to andesite faults. sp2Ta3 crystals doping has significant influence on the structural and thermoelectric characteristics. For this investigation, PVD, that is physical vapor deposition, was selected since it allows the use of S-cultivated crystals for device design without further grooming. In the PVD process, vaporization rates were managed to provide a reasonable quantity of deposition by regulating the temperature gradient and supersaturation. The lack of transportation reduces contamination and provides mechanically stronger crystals. The current work is focusing on their thermoelectric performance, since relevant literature on the vapor development of sulfur-doped platelet crystal is limited. So this is the main work of my research work. The composite charge of sp2T3 was created using an evacuated approximately 10.3 MBAR quartz ampule, length approximately 10 centimeter and diameter 1 centimeter, with the assistance of muffled stove by melting high pure 99.999% components of antimony and tellurium. So I have taken the photograph of that crystal that is grown. It is actually for easy analysis. I kept it on a graph sheet and took a photo. To see, it is approximately 10 centimeter long and diameter approximately 1 centimeter. But when I analyzed about the EDX profile revealing oxygen content, the system uses the characteristic X-rays of different elements to form an energy spectrum. As a fingerprint tool identifies extra phases and is used to assess stoichiometry by analyzing the peak height ratio. In this regard, the ampule was gently broken and the polycrystalline ink dot obtained was subjected to composition evaluation using EDXM model. So this one actually, the graph clearly shows the presence of oxygen. Oxygen was consistently detected as a contaminant in the bulk samples, and hence the prepared compound charge was found to be off stoichiometric. So the further analysis was done. The above mentioned synthesis conditions were improved as an appreciable level of stoichiometry of synthesized charge has to be realized for the preparation of samples with superior qualities. As such, for further trials, the vacuum has been raised to approximately 10.6 bar and the temperature was increased at a rate of 20 degrees Celsius per step for attaining a set temperature of 700 degrees Celsius. After systematic trials and slow cooling, a crack-free shiny ink dot with the dimensions approximately 8 millimeter diameter and 70 millimeter length was successfully synthesized. And this is the crystal that was actually synthesized with the second process. Then surface topography, morphology implies the study crystal forms that encompasses the external features as well as internal structure, knowledge of which permits one to define more accurately the processes in the formation of samples by intriguing the growth characteristics. Surface topography provides a link between the excellence of the grown samples and the synthesis. The experiments were at the temperature. Okay, temperature gradients ranging from 90 to 140 degrees Celsius to optimize the growth condition and tune the shape, configuration, and size of the crystals. And the sp2T3 platelets grown at different temperatures are depicted here. To see actually at 90 degrees Celsius, which is presumably actually very, very small. So I found that it's due to low supersaturation. This is the crystal that is formed at temperature 90 degrees Celsius. At 100 degrees, it was slightly bigger. And to see at 110 degrees Celsius, it is reasonable size crystal. Then AFM image depicting growth hilux. The imaging capabilities of AFM allow the AFM means that atomic force microscopy allow the direct evaluation of local microstructural changes in the material system. In addition to scanning surfaces with a nanometer resolution, AFM can also be used to determine the surface roughness, peak valley height, the force of friction, etc. To analyze the good crystallinity was actually exhibited in the AFM topography. The scan of the sample is actually shown here. And AFM image of each bits also was analyzed. Bits produced have been detected with a high resolution atomic force microscope without dislocations of the vessels. There are no obvious edge hills that signal the lack of overgrowth that might impact the quality standard of the developing crystal inevitably. Weight percentage of elements in the non-stoichiometric sp2te3 chart to see actually when compared with the standard weight percentage. The experimental one was slightly deviating, but still actually the oxygen content was there. But when I unleashed with the XRD pattern of SPD crystal, a peak was shown actually at the side. You can see the intensity variation with the the inclination with the 2 theta. Here actually EDX profile of SPT-T3 crystal, which was grown at 120 degrees Celsius, was quite satisfactory. And it was showing a clear details about the no oxygen content was there, and the chemical composition, configuration of the growth crystals, everything was almost matching with the standard criteria. And the left-hand side, what you see is the crystal. On the right-hand side is the energy spectrum. And this energy spectrum clearly shows the no oxygen content. So the weight percentage of elements in the stoichiometric sp2te3 chart, and you could see here actually very clearly no oxygen content, but it was well matched with the standard weight percentage. So the experimental weight percentage was almost coinciding with the standard weight percentage. So in conclusion, I could say that real-world analysis were performed using GSS software with the EXPG UI interface, and the particular data was refined by GenList version in 32 reinforcement program. In summary, the XRD pattern of Sp2te3 crystals grown at 120 degrees Celsius, where the structures were found out to be hexagonal with the lattice constant A equals B equals 4.2634 angstrom, C is 30.4441 angstrom, which is in compliance with that of existing literature. Hence, the crystals grown are considered and found to be highly stoichiometric, which must be advantageous for enhancing thermoelectric efficiency. So I acknowledge the following references, mainly that was helpful for my research work. Thank you.
Thank you, Ajita, for this
Yes, sir.
presentation.
Yes.
Pankaj sir, if you have any questions or queries.
Yes. First question is related to these references. You have used two old references, 2014, 7, 10, and 11. Why not the recent one?
So I could not get actually proper resources. That is why I analyzed with the existing one. But I could get a more
Try to include the recent papers.
comparable crystal.
So my suggestion is that you have to include recent publication. Hello?
Ajita, are you there?
Yes, sir. Yes, sir.
Okay,
Yeah,
one more
yes,
question.
Sir,
yes, conclusion.
Yes, sir.
So you have
yes,
written
sir.
here the XRD pattern of Sp2te3 crystal grown at delta T 120 degrees centigrade. So what are the different temperatures? This is delta T, na?
Yeah.
So what are the different temperatures you have taken for your study?
Compared to study with the room temperature and the temperature of the crystal.
Huh? Room temperature and?
The temperature of the crystal.
How much it is?
It was grown at 120 degrees Celsius, sir.
No.
Hmm.
You have written here the XRD pattern of Sb2T3 crystal grown at delta T. Delta T, that
Yes,
means
sir.
temperature difference.
Yeah, temperature difference.
So what are the two temperatures?
No, you can see that it was actually the setting was done at 120 degrees Celsius, sir.
Delta T, you know what is delta T? T1 and T2 difference.
Yeah, it is the temperature
So what are
difference,
those T1 and T2?
the environment and the crystal.
Huh?
The environment and the crystal.
So what is though? Environment, that means room temperature is 25 degree or 20 degree. Okay.
Yeah.
So what is the next? Is it 140?
Yeah, it is 140 then.
Are you confirmed?
Yeah, yes, sir. Yes, sir.
So try to focus on this.
Okay, sir. Okay.
And one more thing.
Yes, sir.
Go to the previous slide.
Previous slide, sir. Yeah.
Yes, previous. Okay, this is.
You want this, sir?
Next slide, next slide. Weight percentage. Yes. So this is 38.88 and this is 38.99. So do you think this is valid?
Yes, sir.
Huh?
Yeah, it was like, yeah, comparatively, it is like very close.
So you are nearly to standard value.
Yeah, yes, sir.
So are you
So
getting
when
this, are you getting this experimental value?
Yes, sir. When I found the percentage difference also, it is actually very, very less.
Okay.
Yeah.
Okay, from my side. Thank you very much. Thank you.
Thank you so much, sir.
Thank you, Ajita.
Yeah, thank you so much.
So anybody else? Dr. Rajiv?
Yeah, sir, there the candidate Radhika is there, but I think she left. I'll ask. Neelam? Neelam? Neelam,
Shall I
is there-
stop sharing, sir?
yeah, you can stop sharing.
You can leave.
Yeah.
Neelam, whether Radhika is going to present or not?
Sir, Radhika is going to present, but she is facing some network issue. So she is not able to join.
Okay. So shall we wait or should we end up the session?
I will call her last time. Let me know the problem.
You just
I will-
ask her whether she is able to present or not.
Okay, sir.
Sir, we will wait for some few more minutes. Then if she won't be able to present, then we'll end up the session.
Okay, no issue.
Okay, sir. Thank you.
Sir, thank you so much for listening to my presentation. Shall I leave?
Hi, you can leave.
You can.
Okay, thank you. Thanks a lot.
Thank you.
Thank you, ma'am.
तो बाकी लोग नहीं आए क्या? So Dr. Rajiv,
Please, sir.
we can leave now or we have to wait?
Sir, we'll wait for another 2 minutes because she is there in the meeting, but because of some technical issues, Neelam is calling her.
Okay. And what about rest?
Rest, they are not going to present. You can make them absent.
Okay. Yes, Dr. Rajiv.
Pankaj sir, I think she might be facing some technical issue. So we are ending up the session now.
Okay, thank you.
Okay, sir. Thanks a lot for coming. Thank you so much, sir.
Thank you.